Higgs boson,
चंद्रशेखर लिमिट,
string theory,
न्यूट्रिनोस,
quantum entanglement.
कुछ समझा क्या?
Ever felt bored and confused while reading lengthy physics textbooks or articles?
Yeah, on God, bro.
I'm Arnav,
And I'm Pratham.
and welcome to Quark Talk, where we decode all the complexities and simplify these intricate concepts in physics.
They may have seemed too complex to understand until now.
Alright, Pratham, let's talk about something that might just blow black holes out of the water. Literally. Gravastars.
Gravastars? I mean, that's a weird name. What are they?
So technically, a gravastar is the abbreviated version of gravitational vacuum star proposed by two scientists, Mazur and Motola, in 2001. And they're these mysterious theoretical cosmic objects that are as extreme as they come.
But it's only a theory as of now.
Yes, very much so. So they're filled with pure energy and they're supposedly wrapped in a shell made of the strangest material in the universe.
Oh, that sounds intense, but what makes them so special? And what do they even look like?
So that's the thing. They're not just mysterious, they're mind bending as well. The inside of a gravastar isn't made of normal matter. It's what scientists call supercondensed nothingness.
Supercondensed nothingness. That's definitely one of those phrases that doesn't sound real. What does it even mean?
Right? It's hard to picture, but there's a metaphor to help. Think of particles like quarks, electrons, photons, etc., as waves rippling through an ocean. Those waves need something to move through, like how water carries ocean waves.
Got it. So particles are waves and they rely on some cosmic medium to exist. But happening inside that gravastar?
So, inside that gravastar, the collapse of a massive star compresses this cosmic ocean or vacuum fluid so much that it creates super dense nothingness.
Okay, but even in empty space, there's still some energy, right? So what's different here?
So that's the wild part. In a gravastar, that empty space, that vacuum is squeezed to such an extreme that it holds a billion, trillion times more energy. Yeah. Times more energy per cubic centimeter than regular empty space that's outside the star.
That's absurd. So basically, it's kind of like a black hole.
Yeah, sort of. So the energy inside is so tightly packed that it can't be compressed any further. It's at the absolute limit of what physics allows, by the way.
And what keeps it from exploding outwards?
The shell, it's a ultimate cosmic prison, so called.
Oh my god, these English terms.
No, like it's just a metaphor again, right? So the shell is so strong that it's at the breaking point of what any material can endure. Just how the like energy inside the gravastar is at the absolute limit of what physics allows. So you've got this eternal standoff. The vacuum inside wants to expand, but the shell is not letting it.
So it's basically like two extremes locked in a stalemate.
Exactly. So here's the kicker. Gravastars are basically indistinguishable from black holes, especially for humans like us,
Yeah.
and especially because they're far away.
Yeah.
They're cold, they're dark, and they're massive. Both of them warp space and trap light and create accretion disks and even slow down time near them. Gravastars are everything we associate with black holes.
But if they're so similar, how would you even know if you're dealing with a gravastar or a black hole?
You might not, but let's say you're on a space journey and you're like falling into a gravastar, okay? So you'd be torn apart by gravitational forces before you even reach the shell. So if you're not torn apart, then you're probably dealing with a black hole.
Okay, that sounds a little brutal. And what happens after you're shredded?
So your remains would hit the shell and your atoms would most likely dissolve into the vacuum energy inside. Very less of a difference, but the gravastar would still get a bit bigger and a bit more massive.
So it's like infinitesimal. Like
Yes,
the
definitely.
calculus type thing.
Yeah.
So falling into one would make it stronger, but just a little smaller. But that's terrifying if something big falls into it, though.
Yeah, it is. And they might be theoretical, but if they exist, they are one of the most extreme things in the universe.
So what's the point of all this? Is it just another speculative idea or like a wild theory for the sake of it?
Not really. So let's talk about how the universe creates its most extreme objects, like supernovae and black holes and gravastars. So it all starts with massive stars and their dramatic deaths.
You mean supernovae, right?
Exactly.
So those stellar explosions that light up brighter than entire galaxies. So here's the quick version of them. When a massive star runs out of fuel, its core collapses under the force of its own gravity in less than a second.
And as the core collapses, the star's outer layers come crashing in. They bounce off the core and explode outward in this like spectacular event, right?
Right, but what happens next depends on how massive the star was to begin with.
Yeah, it can go one of two ways. The core might compress into a neutron star, which is insanely dense but stable.
Or the star could take the more extreme route, which is becoming a black hole. This is where the core collapses so completely that it forms a singularity, a point which has no size but infinite density.
And that's where the universe so called stops playing by its own rules. Time and space get flipped totally, like completely. We've spoken about it in episode 2, I think. What are black holes? So, and everything just breaks. But there's a third option that's even stranger, a gravastar.
Oh, so a gravastar. But how's that different then?
Well, instead of collapsing into a singularity like a black hole, the star's core gets crushed so intensely that particles break down and transform into pure energy.
So the core becomes what? An energy bubble?
Exactly. So this bubble is like a mini universe, and just like our universe, it wants to expand outward like very violently.
But the collapsing star around it is trying to crush inwards at the same time.
And that's another cosmic battle. It's an unstoppable force colliding with an immovable object. The energy bubble expands, but the star's mass contracts. And in that clash, they forge something entirely new.
And this something entirely new is a gravastar, right?
Exactly. So the process suddenly stops, and what's left is this bizarre object that is theoretically possible, but it's unlike anything we've ever seen.
Okay, but what does an actual gravastar look like?
So that's where things get even more bizarre. So just like black holes, they can have pretty much any mass, like insane amounts of mass. But let's just picture a typical one about the size of the like London metropolitan area.
That's specific.
Yeah. So it would be as that the size of a gravitas the size of the London metropolitan area would be have the mass of like let's say I think 10 suns.
Whoa, that's mad. But here's the kicker. The shell of the gravastar is the coldest thing in the universe. It's only a billionth of a degree above absolute zero.
Wait. Colder than the cosmic microwave background, colder than the black hole's shell itself, like so-called shell, like the yeah. Actually,
In deep infrared, the cosmic microwave background would glow very brightly next to the gravastar. It's that cold.
but how's that even possible? Don't like all atoms have to jiggle at least a little?
Here's the thing, the shell isn't made of atoms. It's composed of a completely new type of matter, which is something so extreme we don't even have a name for it yet.
So this mystery matter is what like super dense.
Not quite. In fact, the shell is so thin that regular atoms would seem enormous next to it. But
Wow.
despite being ultra thin, the shell is incredibly strong.
So like the like special form of carbon fiber kind of thing that we have today. Like it's very thin but it's extremely strong.
It's much stronger than that.
Yeah.
It's strong enough that if you try to stretch the shell by even a meter, you need the energy of an entire supernova.
So don't try pulling on it, I guess. But what about the inside? What's happening there?
I mean, that's where it gets even weirder. The interior of a gravastar is completely empty. A perfect vacuum. It has no atoms, no particles, no waves.
So just nothingness?
Not quite. Even though it's empty, the vacuum is alive with the most fundamental kind of energy in the universe. It's boiling with this raw primal energy even in the emptiness.
So Gravastar is basically a paradox, right? It's empty but it's powerful. It's thin but it's indestructible. It's cold but it's made from something hotter than we can imagine.
Exactly. It pushes the boundary of what we thought was possible.
So the point we're trying to make is that, like, let's say black holes they were suggested more than a century ago as an abstract solution to the equations of gravity.
Correct.
And for more than 50 years, they were considered mathematically valid but too absurd to be real. Like who would even believe that they were real, right? Few people in the world actually believed that they actually existed. But scientists kept working on paper and we saw weird things. Then we saw stars being thrown around by invisible titans as we looked through the telescopes
Yeah.
and our, like for example, James Webb Space Telescope and etc.
Yeah.
So we saw light stretching around invisible gaps in the sky. And as our technology and theories improved, we even sort of took a picture of them, right? M87.
We have evidence for them and they fit our theories, and nowadays it's kind of common sense to accept black holes as real, and they are extremely elegant and fascinating, but they've also created a lot of questions that have traumatized physicists for decades. I mean, Singularities literally break our best understanding of physics. They seem to delete information which shouldn't be possible.
Yep. Stephen Hawking would
Yeah.
definitely beg to differ.
Yeah.
Like, he really wants the information to be safe. So, gravastars are like a relatively new idea without any of those problems. They don't need singularities that break physics or delete information. They solve the puzzles of black holes, but they too create new problems, like weird exotic matter for the incredibly cold and tight shell, or the super dense nothing to make a supermassive empty core. But just like black holes, they do work on paper and they also fit what we see in the sky.
So, are they real? And will we ever know? I mean, actually, there is a way to find out about that. So, black holes have an event horizon, while gravastars have a physical shell made of matter, which means that they behave very differently when they smash into each other.
So we can also call a black hole shell like its event horizon. Like a black hole's event horizon its shell, even though it's not like actually a shell, but like whatever. So the collision of two objects as massive as they are, black holes and gravastars, creates huge amounts of gravitational ripple waves. And these are again ripples in space-time that travel at the speed of light. We've spoken about this as well.
Yeah.
So you can think of them as the music of cosmic cataclysms. The collision of two black holes should sound like a bass drum, like a deep thump that stops quickly. Like, because they don't have any shells, right? It's not like a physical matter. It's just like technically like not like they're merging together, like you can say slime or like what? Yeah, something like sponge. Okay, so two sponges rather than like cement walls is what gravastars would be. So like gravastars colliding would be like a gong kind of thing, leaving subtle echoes behind.
And scientists are listening for these echoes in the music of the cosmos. So,
Oh.
unfortunately, black holes and gravastars are surrounded by such strong gravity that it swarms most of the sound. It's like trying to tell two instruments apart through a thick wall of concrete. You need a very sharp kind of technology for that. And while we've made incredible progress in that for the last few years, we're not quite there yet.
So this is where we'll end the story because gravastars have the potential to answer some of the biggest problems in physics. Or they're just another idea for a discard pile. But that's why we try science, right? That's why we do science. To understand that everything is different from the way we thought it is until the way we truly understand the nature of reality.
Yeah, discovery is an ongoing process.
Exactly.